Hi, hello everybody, and welcome back to another installment of the Damage Control Assistant Senior Enlisted Curriculum. I'm Lieutenant Timothy Mueller, and I'm going to be the instructor for Lesson 1 in Chapter 4, where I'm going to go over statical curves and stability of a vessel. Now, so far in previous lessons, we had talked about initial stability and then overall stability of a ship, but we only really talked about initial stability, where we have the metacenter staying in the same spot as we incline a ship 0 to 7 or 0 to 10 degrees. What happens when a ship goes beyond that? Well, we know the metacenter moves along the metacentric. However, it seems kind of complicated as to exactly how can we use that information and get an answer where if we're trying to make recommendations for abandoning ship or for moving weight, how can we make those recommendations and make solid actions on those in an easy, clear way to see on a graph? Well, I'm going to go over that in this chapter, and this is called Statical Curves of Stability. So as we look here, we have these two ships, and we know that if we're at the initial stability, we have a metacenter that's up here on the center line, right above the center of gravity, and the center of buoyancy swings over. However, if we stay in this inertial frame, or if we stay in this solid frame where the waterline stays still and the boat moves around the waterline, you'll notice that G actually moves horizontally, not along the ship, but in reference to the buoyancy itself. So that GZ is not something that we can just immediately calculate or look at and say, okay, yeah, it's going to be this at 15 degrees or this at 20 degrees. Because over here, we'll have G move and then B moves at a much different speed. So we have to find some way, or there has to be some sort of a graph that actually has this information on it. With all of these situations considered, from 0 all the way to 90, even further than that, 100 and 110 degrees, there's a graph or a chart that naval architects use in order to get all the information about a ship's righting arm out to the manufacturers. And that's going to be this graph right down here. This is a three-dimensional graph with this axis being the displacement, and then this axis being the inclination in degrees. The vertical axis here is GZ in feet. So what this graph is, this is a very complicated graph, and you won't see this unless you're a naval architect in your software. But what this is just imagine a flat grid, kind of like on the floor, where one side tells you displacement, and then the perpendicular axis tells you degrees. Then there's going to be a point above that grid. So at a certain displacement and a certain degree of inclination, you're going to have a value of your righting arm. That's what this is. If you imagine this square here, this isometric square, as that grid, and then the GZ is just a value above that grid. So instead of having a two-dimensional graph, we have a three-dimensional graph. Given two variables, displacement and degree of inclination, we can get GZ for a whole wide range of displacements and degrees of inclination. But now looking at this doesn't really give us, the user, the operator, any information about our ship. It's very convoluted, and trying to put this on a piece of paper is very difficult, especially if you're trying to measure exact values of your GZ, your righting arm. So how does the naval architect get this into a way that we can understand really quickly? Say we take on damage, it's going to be a very stressful situation. You don't want to be doing any calculus or anything crazy when you're trying to get measurements of your ship's stability. So they give us this, and this is the cross curves of stability. What this graph is this chart, or this graph here, but imagine we're standing on this axis, the displacement axis, and we're looking in. You'll see all these, not straight lines, but they're kind of curved lines here, 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 and here, in this example. These are called cross curves of stability. And they go across the different curves, the statical curves of stability for a ship at a certain displacement. So a ship at, we'll say like 1,200 long tons is going to have a curve that looks like this. One at 1,400 is going to have one like this. 16 and 18, so on and so forth. These cross curves tell us that at, for this example, 10 degrees, a ship going through all these displacements is going to have a righting arm of this value. So as a ship as a ship goes through its displacements from a light ship condition all the way to a full load, or maybe even beyond that, it's going to have different values of its righting arm at 10 degrees. Then there's going to be another cross curve for maybe 15 degrees, 20 degrees, 25 degrees, then it goes 30, 40, 50, all the way to 90, 100, 110, whatever it might be. It all depends on the shape of the ship's hull. That information is right here. So we see a line here. This is for 10. This here is for 20, 30, 40, 50, 60, 70, and 80 in this example. So all we have to do is find our displacement, and then say we know our displacement 1,600 long tons. Well, we got 1,600 right here. Then we just have to draw a line straight up, and that's going to give us the value of our righting arm at that displacement, 1,600, all the way through all the information that's given to us by the naval architect, which in this case is 0 degrees, because at an assumed kg, you're going to assume that your center of gravity is right on your center line, so we're going to go from 0 all the way to 80 degrees. Once you do that, and you plot out those points, you're going to get a graph that looks just like this. And this is a standard look for a statical curve of stability for a ship. You'll see these steps 1 to 3 and step 4 and 5 right here. And I'm going to get to that in a second. However, I'm going to start talking about these terms here on the left of the screen. Now, as I mentioned, this graph right here is a very typical look for a statical curve of stability of a vessel. This is like, say we have an assumed kg of 12, and I'll get into that in the later video, what that really means and what we have to do to correct if we don't have a kg of 12. But you're going to see a curve that looks kind of like this. And these terms on the left here are all things that we can get readily from this curve. So let's start from the beginning. We have range of stability, and that's pretty much exactly what it sounds like. Range of stability is where we have a 0 righting arm, goes up into the positive, and then where it comes back to 0. So if we have a 0 righting arm at 0 here, assuming the center of gravity is directly on the center line, then we have positive stability all the way through here, and then it comes back to right around 80 in this example. That would be our range of stability. The range of stability would be from 0 to 80. Now the next two terms are very closely linked. We have angle of max GZ, or angle of maximum righting arm, and then we have the danger angle. So the angle of max GZ, angle of max righting arm, is something that we can just take a look at the chart, or take a look at the graph and say, okay, that's my angle of max righting arm. And that's exactly what it sounds like. It's the point where our maximum righting arm exists, or where the righting arm, GZ, is at a maximum. So we look at this curve, and all we got to do is find the very top. So we look here, it's going to be right around here. That's going to be the point where our maximum righting arm exists. If we want to find the angle of maximum righting arm, we just read where that point is off our horizontal axis. So here, we would drop a line, and it'd be right about 54 degrees. So we know that our angle of maximum righting arm is 54 degrees. If we want to know what our maximum righting arm is, so we don't care about the angle, we care about the actual righting arm itself, then we just take that same point and we read off of this axis right here. And this would give us 2.8 feet, 4.5 feet, whatever it might be, typically in feet or meters. But this is going to give you a length if you're looking for the righting arm, because remember the righting arm is the distance from G to Z, so we would expect it to be in feet or meters, something like that. And then the angle of maximum righting arm is going to be an angle, and that's where you take that point and just drop it straight down. Now the danger angle is not something that you can just look at the curve and immediately know what it is unless you know your maximum righting arm. And the danger angle is defined as 1/2 of the angle of maximum righting arm. So knowing that, we know our angle of maximum righting arm is 54, so if we just divide that by 2, we get 27. So our danger angle, is going to be right around 27. Now what does this mean? The danger angle is something that's more of a factor of safety when it comes to recommending abandoning ship. When you have a ship that lists all the way over and then eventually hits its angle of maximum righting arm, it is very, very, very likely to capsize. So if you take damage in battle, or if you ground, hit rock, something like that, and you start listing over, if you list to the danger angle within 10 to 15 minutes, it's typically known through experimentation that the ship will capsize. It just has this momentum about it that'll carry it all the way to this point where it'll eventually capsize. We have deck edge immersion. Now, if a ship lists to the danger angle over several hours, then it won't necessarily capsize. We say if it lists there to 10 to 15 minutes, then it'll capsize just because of all that battle momentum. Now, if it lists over there in, like I said, several hours, it's been typically found that ships that sink will sink because of a violation of their floodable length. And we'll get into that in a later video. However, just remember, your danger angle is 1/2 of your angle of maximum righting arm, and the danger angle tells you that if you list to that angle in 10 to 15 minutes, then your ship is very likely to capsize. It just gives you this much time for you to start to recommend to the captain to abandon ship and start making preparations for abandoning ship. All right, next up, as you see, is the point of vanishing stability, a very simple one. It's just where our stability goes from a positive to a negative. In this example, it's going to be right at 80 degrees. So it's going to be the very end of our range of stability. All right, next up, we have angle of conjecture. And angle of conjecture is, by definition, the inflection point in the graph before you get to your angle of maximum righting arm. That means that the second derivative is 0. However, without getting into the calculus, it basically means that the angle of conjecture is the point where the chart goes from concave up to concave down. So basically, you think like a cup. If the cup can hold water, it's concave up. And if it spills water, it's concave down. So we see that the graph it starts at 0, and it's increasing all the way to its angle of maximum righting arm. But however, we look at the behavior of this line, we see that from here to about here, it's increasing, and then it's increasing even more as we keep going along, we keep marching along those angles. Then, once it hits this point, as we keep going along our angles, it's still increasing, however, it's increasing less and less and less, until it eventually gets completely flat at that top point here. This point, where it goes from concave up to concave down, is our angle of conjecture. And to read the angle of conjecture, you just drop a straight line down, and it's going to be about 39, 40 degrees for this. So just remember, the angle of conjecture is where you go from holding water, think of a cup, holding water, to spilling water. All right, next up is something that's called the Radian Line. On any actual printed chart of this, you're going to see a dotted line that extends from the angle 57.3 all the way straight up. Now, why 57.3? It seems like a pretty random number. Well, it's not. We're going to have another video. Actually, the next video is going to be all about this Radian line and kind of proving and determining why we have this line. However, as a quick introduction to that, we have this line, the Radian line, at 57.3 degrees. Now, a ship from 0 to 1, 2 to 3 degrees is going to be very, very linear. There's going to be very low deviation from this line. If we take that line and then independently from the stability graph, we just extend that line all the way to the Radian line, that height at that Radian line is going to tell us our GM at that point. So we take this here. So if we imagine that this here is a straight line, because we know that in like 0 to 3, 0 to 2, it's a very, very straight line. And if we extend that line, separate from the statical curve of stability, we just take this and we just go all the way out to the Radian line. That point right there is going to give us some height. This height is the metacentric height of the vessel. And like I said, I will prove that and derive it in the next video. However, just think. Take your initial readings, take a ruler, and just place it tangential to that line, and then just draw it all the way out. Right where it hits that line is going to be your GM of the vessel at that condition, so that displacement at that time. All right, so now that we've talked about these statical curves of stability a little bit, what are the steps in order to actually make one of these graphs? Because it's going to change with every single displacement, and it's also going to change with different centers of gravity. However, we'll get into that in a later video. But let's just find how do we draw the initial loading condition of the ship. So we'll see step 1 to 3 is right here with the cross curves of stability. Step 1 is going to be find the cross curves of stability. This is going to be this chart or this graph right here. And it is going to be found in either your DC book, your damage control book, or some other publication given to you by the manufacturer. Step 2 is going to be find your displacement. This is something that you can find from your mean draft, your forward and aft drafts, and then go into your draft diagrams and functions of form, and then actually calculating your displacement. Step 3, once you have your chart here and you have your displacement, step 3 is finding out your displacement and then drawing a vertical line at that displacement. So let's say we are 1,600 long ton. We're drawing 1,600 long tons. On this horizontal axis goes 12, 14, 16, 18, and 20. So 1,600 long tons, and take that, and I'm just going to draw a straight vertical line all the way through all of our cross curves of stability. What that is doing is it's basically taking, at 1,600, we are now drawing a line through all those cross curves of stability. So we're extracting just the information that we need at 1,600. Now we see all this, and we just make points and make a mark of where our vertical line meets every single cross curve for each degree. So at 10, we have this point, which is right about 1. We have this point at 20, right around 2. At 30, we have right around 3, 2.93. 40 is right here, right around 3.8. 50, right around 3.9 or 4, and you continue down. You go 60, 70, 80, 90, 100, whatever else might be. Every single cross curve stability graph is going to be different for each ship and each different hull shape. So now that we have all those dots, we now know at our displacement and at each angle, not every single angle of inclination. However, we have a lot of information in order to draw a graph. Then we go to a blank set of axes. It's going to have righting arm on the vertical axis and then angle of inclination on the horizontal axis. Now we know our righting arm, which is going to be the vertical axis here as well. And we also know different values at different degrees. So all we do is we take the information on these dots and we just translate it here. So we would take our information at 10 degrees, it's about 1 foot. So we say 10 degrees, we would find where 1 is on this this vertical axis. Then we would draw a point there. Then we go to 20, then 30, 40, 50, so on and so forth, and we would finish that graph. That is step 4. And then step 5 is just drawing a smooth curve through all those points. That way it gives you a little bit more resolution when you're trying to read exactly right between points. So if you say the cross curve gives you 20 and 30, you can read 25 off of a smooth curve. All right, so you're probably thinking this video is jam-packed with a lot of new information, and you're not wrong. There's a lot of information. However, it's extremely important that you understand everything in these statical curves of stability because it tells you a lot about your ship and what kind of damage it can survive. Now let's go through an example problem and actually see all this in action. We're going to go through the steps. We're going to use our cross curves of stability, and we're going to make one of these statical curves of stability graphs. So step 1, we had talked about find your curves, your cross curves of stability. That's going to be in your DC book or some other publication given to you by your manufacturer or the manufacturer of your vessel. So this here, we're going to assume that this is our cross curves of stability for the ship. So step 1 is now done. Step 2, if you'll remember, is to find your displacement. This is something you can get from your draft diagram, functions of form, or some other thing that you have from your ship's manufacturer that will tell you what your displacement is. It's typically going to be based on your drafts, your aft draft, your forward draft, mean draft, whatever it might be. So you're going to have to find your displacement. In this prompt, we're given a displacement of 2,400 long tons. So we know our displacement. Step 2 is complete. Now we have to go to step 3. Step 3 is to take both of these and now kind of merge them together and extract information. We do that by drawing a vertical line at our displacement through all of our cross curves. So if we know our displacement is 2,400, and here on our cross curves, our horizontal axis goes from 1,800 all the way to 2600, we know that at 2400, that's our displacement. So we have to find our writing arm at certain points of angles of inclination for that displacement. So we do that, like I said, draw a vertical line. So 2400 long tons, we can go right here, and it's going to draw a vertical line right through all of our cross curves. So now I have to look at that line, find out where it crosses each of those cross curves, and then just kind of save all that information for later, where I'm going to be drawing it right on this set of axes right here. So I look at this. I kind of just march through the angles of inclination. So I start at 10. At 0, we have 0. Then at 10, it meets right about there, which means at 10, it's about 0.7. Then at 20, we cross right there. And that's at about 1.6. Then 20 to 30, here, read it off that axis, it's right about 2.5. 30 goes to 40 right here, then 50, 60, 70, 80, and then 90 right there. So we're going to have all this information, and I'm going to write it all out in a table right down here, and then we're just going to take the angle of inclination, which is going to be on this axis, and then we're going to draw a point where the writing arm is whatever value we've extracted from the cross curves right above that angle. So like I mentioned, at 10, we have right around, 0.7, 0.6, 0.7. So we would just draw a point right around here. And when you have all this given to you by the naval architect or your ship's manufacturer, you're going to have a lot more precision when you get to it. However, in just drawing an example here, I don't have too much precision on my axes. All right, so I've extracted all that data from my cross curves, and then here on this axis, I just wrote the value of my writing arm directly underneath all these angles. So I got 0.7, 1.6, 3.5, 3.1, 2.1, 1.2 at all these different angles. And the height of these dots above this horizontal axis just corresponds to that value along here, because that value is my writing arm at that angle of inclination. And this vertical axis tells me, the scale for my writing arm. So I just draw all these points. So that's step 4. Just draw all your points. Now that gives you enough information to go to step 5, which is just to draw your smooth curve. So all you do is you start at 0. And you start at 0 because we are assuming that the center of gravity is directly on the center line of the ship. You'll see here, I assumed kg equals 12 feet. When we get into sine and cosine corrections, we're going to see exactly why we need this information. But right now, with what we're trying to do here, we don't need to do any corrections to it. So we start at 0, and we just draw a smooth curve through all these points. So we're going to start here. It's going to go here. Right like that. And so we see we got 0.2 for a writing arm at 90. So our point of vanishing stability is going to be a little bit to the right of 90, which means our ship will actually stay over. It can actually right itself past 90 if it happens to roll over that far. So now looking at this chart, we now know a lot about this ship. We know our angle of maximum writing arm occurs somewhere around 50. And that makes sense. We take a look at our cross curves of stability, and we see that our maximum, the highest dot that we got, was at 50. So after drawing our smooth curve, we would expect our angle of maximum writing arm to be right around 50. So if we know that is our angle of maximum writing arm, we know that our danger angle is half that, so we're right around 25. So if we take damage and we start listing, and we're listing to 25 degrees within 10 to 15 minutes, then we know the ship probably has just too much momentum and it's going to keep going, and our damage control efforts are probably not going to help. So we now have enough time. The ship is going to start listing from 25 to eventually capsizing at 50, all that time to make preparations for abandoning ship. We also know our range of stability is going to be 0 to maybe around 92, 91 degrees. Our angle of conjecture is going to be somewhere around there, right around 22, 23 degrees, something like that. And then with our radian line, we know that radian line is going to be at 57.3 because 1 radian, which is another way of measuring angles, equals 57.3 degrees. Draw this all the way up. Then we look at the initial line of the curve. Take that, draw it all the way out, and that's not the straightest of lines, but right where they cross, right where that line, that extended initial stability, crosses that radian line, that is going to be our GM. And so we read that as that dot is over here right around 4, which means that the ship's GM, in this case, is 4 feet. Now, is that a good thing or a bad thing? It depends on the ship. If you have a ship that normally sits right around 3.8 as a GM, your metacentric height, then that's fine. However, if you're a ship that typically sits at something like 12 feet, now if you only have 4 feet, that's a major degradation in your initial stability. You might not be able to perform the job that the ship was built to do. Maybe if you're a barge, you don't want a GM that's low. Maybe you need, according to your DC book or your ship's manufacturer, maybe you need to maybe you need to obtain a GM of 8, let's say, in order to have a stable base for your crane. There's a lot of information that you can get from these charts. So in this example problem, we had created one of these stability charts from our cross curves of stability. However, we know that our center of gravity is shifting constantly. If someone moves from, or just a normal person just walks from a lower deck to a higher deck, that's a weight shift. And so we know our center of gravity is going to move up. Depending on the displacement of that ship, it could be a serious move. If it's a small pleasure craft or a small sailboat, like someone climbing up the mast, that's a large shift in the center of gravity. If it's a large ship, like an aircraft carrier or an oiler or something, then that's not a very significant change at all. So we have to use this information, assume kg equals 12 feet, find out how far off our actual center of gravity is, and then we can correct this graph. But that's going to be in a later video. And we're also going to learn how to correct it for off-center. So we take our real-world situation that our ship is in, and we can correct this curve, which is just some boundary condition that the naval architect had at 12 feet, correct that to any possible situation that the ship might be in. But like I said, that's going to be another video. At this time, I'm Lieutenant Timothy Mueller, and I hope you have a great day.